All right, welcome to day 18. We're going to be looking at alternating series airbound today. First one on the homework. We wanted second degree, so you had to do out to your second derivative. Sub in 0, you get 0 at those derivatives are 1/2 and negative 1/4. Then down there where it says P2 of x, you can write out your second degree polynomial. If you put in, now, if we want square root of 1.4, keep in mind our original equation is square root of 1 plus x, so we're really only putting 0.4 in for x. So that's why this is just P2 of 0.4. And then we need our next derivative. So here's our third derivative here over on the right. We're on the integral from 0 to 0.4. So the bigger things that are subbed in for x make the denominator larger, making the value smaller. So our biggest value of that derivative will be when x is 0 on the interval 0, 4. So when you put that in, you get 3/8 for your value of m. Then you got your 0.4 minus our center of 0, absolute value to the third, over 3 factorial, because that was our next factorial. That gives us 0.0004. And usually you see this written like in the box there, where you just leave it subtracted and added, and then we know square root of 1.4 is somewhere in between there. So if we want to be accurate to 3 decimal places, that's really 0.0005. This website here is a good explanation of why we do that, if you wanted to check that out and were unsure. Okay, it's basically how when we round, if you're going 3 decimal places, our answer then is at most off by 1 more decimal place out and a 5. Because if it was like a 4-9, it would round down. And if it was a 5-0 or greater, it would round up. So if we take m to be 1, because we're working with sign, so we know that's a max. 4 would be our next degree, 4 factorial, and then we're just solving for x there. So multiply the 4 factorial over, take the 4th root, and that'll tell us for x what our bounds are. Similar idea for cos, but we had 4th degree here, so the next one would just be 5. That's the only difference. Oh, and I guess the other difference is we wanted to 4 decimal places, so we would have 0.00005. So we're working with sine again, so we want our m to be 1. We've got 5th degree, so then the next degree would be 6. Notice that we're staying from negative a half to a half. So we want to think what would give us that largest, and it would be at a half for sine. And because it's absolute value, you really could have used either of them. And then we get our 0.0000217 there. Remember, keep it at the 3 significant figures if you've got a bunch of zeros. So we want second degree. So that means we want to, when we do our Lagrange error, we want to be working with the third derivative. So we get that eventually there, that 2 over 1 plus x all cubed. So we got to think on the interval from negative 0.2 to 0.2, how will we get a maximum? Well, we want our denominator to be as small as possible, so that would be at the negative 0.2. So the negative 0.2 will give us our m value. When we fill that in, we get 125 over 32, or 3.90625. So it's kind of subjective of what you use, because, I mean, you could have hypothetically said, oh yeah, 4 is a nice number there, and then you'd get a little different answer. So we'll see the ones later on in the homework that are most similar to the AP that force everyone to get the exact same answer. So because the absolute value, you can either put 0.2 or minus 0.2 in there. We had determined that the minus 0.2 is the actual maximum, so it might have made more sense to put the minus 0.2 there just to be consistent, but you get the same thing. We've got our m value, and then you got the power of 3 and 3 factorial, because those are the next ones. So for e to the x, remember e to the x's derivative is always e to the x. So when we are looking at the fourth derivative, because that would be the next derivative, we'd still be working with e to the x. That's a growth function, so the max would be at 0.1 on our interval negative 0.1 to 0.1. So that's like saying the 10th root of 2.7-ish. So 2 or 3 could be good ones. I used 2. If you used 3, you would have a slightly different answer. So we got our value, we used 0.1 minus the center, raised to the next power, and over the next factorial. So 4 and 4 factorial. So we are working with the function cube root of x, essentially. The value we'll be subbing in is 10, and our center is 8. So we need to go to the fourth derivative, which is what we get here. That x is really going to the denominator. So if we want it to be big, we want that denominator to be small. That's why we'd sub the 8 in to get the max value. And you get this fraction here, but we always put m in as an absolute value. Then we got the 10 minus 8 because that's where our approximation is. And then our next power and next factorial we have are the 4s. So these next three are the biggest ones to focus on the homework because these are how Lagrange error comes up on the AP exam. On the AP, they want everyone to use the same m value. So written in these ways would force everyone to use the same m. So to approximate f of 1.4, the best we can do is a second degree polynomial because we only know out to the second derivative. So that's what's built there. We have the 8 plus 4 times x minus 1 to the first over 1 factorial really, and then the minus 2 times x minus 1 squared over 2 factorial. So that was the best we could do. Then sub in your 1.4 and you get that 9.44 approximation. Well, now for our error, our next derivative, the third derivative, they tell us what the max value of that could be. They tell us it's 10. So that guarantees that everyone's going to use the same m value. Then you just do your 1.4 minus 1 in the absolute value, raised to the next power over the next factorial, and this would guarantee that everyone gets the same thing. So being able to do something like that is how Lagrange error will show up on the AP exam. A couple other variations of that. So we should be able to do a second degree approximation again. We were working with -1, so sub in -1, you get back 7. So then fill everything in. Our max value of m for the next derivative, they told us was 2, so you got 2 for m. -1 minus 0, which was our center, raised to the third over 3 factorial, so we get a third. Now they want us to prove that it can't be 8.75. So what we do now is we take our approximation, subtract the 1/3, the error, add the 1/3, and we know the f of -1 has to be in between there. Well, therefore, we proved f of -1 cannot equal 8.75 because it doesn't fall in that window. And the next one, you were doing a similar idea. So we had good to the second derivative so that we could do a second degree approximation. Fill in your 1.8, you get -0.24. M they want us to use is 5. Fill in your 1.8 minus 2, which was our center, raised to the next power over the next factorial, the 3's. So we get that 1 over 150 for the error. So subtract that and add that to our this should say a 4 here. Subtract that and add that to our approximation. And notice that we're guaranteed that g of 1.8 has to be in between two negative numbers. So therefore, we've now proved that g of 1.8 has to be negative. So those last two parts B's are just variations on how you could use the span that it could be, the interval that it could be, to prove something. Now our bonus from the other day, so we want the approximation for natural log of 3/4 to be less than 0.00001. So do several derivatives and see if you can figure out the pattern. Well, notice 24 is really 4 factorial, 6 is really 3 factorial, 2 is really 2 factorial. So the numerator is always 1 less factorial. And so our m needs to be the maximum value of the next derivative. Well, we're working with 1 because 1 is what they wanted us to center it at. So when you sub in um, 1 for each of those derivatives over here, that's why we got those in the numerator. Well, that was always 1, again, 1 less than the value of n for our factorial. So with the Lagrange, we always work with the next derivative. So we'll have, instead of n plus 1 factorial in the numerator, we will just have n factorial. And for x, we would fill in the 3/4. Then that's over the n plus 1 factorial, because that was actually 1 power more. And then what I did is I neatened that up. Dividing by 3/4 to the n plus 1 is the same as multiplying by 4/3 to the n plus 1. And then we've got the 3/4 minus 1 in absolute value raised to the n plus 1. We wanted that to be within 0.0001. So put that in a graphs page, do a control T, and the first time that happens is with the 6th degree for n. All right, we're going to be in the day 18 notes. So first, a little review with alternating series. We saw in the first half of the unit that the alternating series test told us that an alternating series will converge if the terms will approach 0 as n goes to infinity. By the terms, we just mean the absolute value of them. And that if each successive term is less than the one before it. So we're going to see if whether or not these will converge by the alternating series test. So if we write out a couple of these, when we sub in 1, we'll get -1. When we sub in 2, we'll get 1 over square root of 2. When we sub in 3, we're going to get -1 over radical 3. So it looks like as n approaches infinity, of our terms does approach 0, so that's good. And it looks like each successive term is less than the one before it, so that's good as well. So therefore, because it's alternating, we can say it converges by the alternating series test. In the second one, let's write out some terms. We sub in 2, we'll get a positive. We'll have 2 over 2 minus 1, so that's 2. Sub in 3, we'll get a negative. 3 over 3 minus 1, so we'll get -3/2. If we sub in 4, we'll get 4 over 4 minus 3, and it's a positive, so +4/3. So we are alternating. So let's think about our limit as n approaches infinity of our terms. Well, when you ignore the negative, notice we have same degree, so it'd be ratio of leading coefficients, which is 1. So therefore, this diverges by the nth term test. Because if something's going to converge, the individual terms have to approach 0. Next one, use the alternating series test to determine whether or not this series converges. So it's definitely alternating. So we've got to see is each successive term less than the one before it? 1/4 is less than 1. Uh-oh. 1/3 is not less than a fourth. 1/5 is not less than a 16th. So this doesn't apply. So we can't use the alternating series test. So we got to see if there's something else we can use. Well, let's see if we can write this as a series. And if you look, the positive parts and the negative parts have different patterns. So let's think of these as groups. So for the first fraction, we're 1/1, 1/3, 1/5, 1/7. So for that first fraction, it's always 1 on top. It's jumping by 2 every time. And let's say we'll start with n equals 1. So if you sub in 1 right now in the denominator, you get 2, so we'd have to subtract 1. Let's see, when we sub in 2, we'd get 4 minus 1, we get 3, so it'd give us that one. Sub in 3, 6 minus 1 is 5, so we get that one. So that works for our first fraction. For the second fraction in each pair, it's a minus. We've always got 1 on top. We got 4, 16, 36, 64. Well, 4 is 2 squared, 16 is 4 squared, 36 is 6 squared, 64 is 8 squared. So we always have even numbers squared. So what we would want is we would want 2n, the quantity, squared. Because when we sub in 1, it'll really be 2 squared to give us 4. When you sub in 2, it'll really be 4 squared to give us 16, and so on. So this is what we're working with. If we get a common denominator, we would end up with 4n squared minus 2n plus 1. And then we'd have 2n minus 1 times 4n squared. Well, if we multiply out the bottom, we'll have 8n cubed minus 4n squared. So we would want to do this with a comparison test. So let's compare to series n equals 1 to infinity. The gap between our degrees is 1. So we're going to compare it to 1 over n, which diverges since it is the harmonic series. So we'll do the limit comparison test. We're going to do the limit as n approaches infinity. We're going to divide our series in the nice one. When you divide by 1 over n, it's the same as multiplying by n. So it's just everything is going to have a power that's 1 bigger in the numerator. And we're looking to hopefully be a positive finite number. If we are, then this will do what our nice series does. Well, now same degree, so this is going to end up giving us 4/8 or a half, which is a positive finite number. Okay, it's bigger than 0. So we can say, therefore, our series, n equals 1 to infinity, we had 4n squared minus 2n plus 1 over 8n cubed minus 4n squared diverges by the limit comparison test. So if alternating series test does not apply, try our other tests, and that was just a little bit of review of ones from the first half of the unit. Well, the other thing we looked at with alternating series was the alternating series error bound. And that said that our maximum possible error was just the absolute value of the next term. So in this first example, it is alternating because we've got the -1 to the n. if we want to find our error of S5, our fifth remainder is going to be less than or equal to the absolute value of our sixth term. So that's just the absolute value of -1 to the sixth over 6 factorial, which is the same as 1 over 720. So this is saying if you do the fifth partial sum, we know you're going to be within 1 over 720 of the infinite sum, the sum of the series. Well, then we often had questions, how many terms do you need to be accurate within a certain amount? So within 3 decimal places, we want to be less than or equal to 0.0005. And again, that's due to the rounding. You're definitely not going to be bumping up or down by more than 5/10,000ths when you round. So we want our next term to be less than that. The way I suggest to do this is identify the error term and then know it's one before. So we don't care about the minus because we're doing absolute value. So we need 1 over n to be less than or equal to 0.0005. Well, this is really 5/10,000ths. 5/10,000ths reduces to 1/2000th. Now again, remember, we're finding n, which is going to be the error term. And then we know we have to go 1 before. And the reason I suggest to do it this way is for when we, in a second, work with sines and cosines where it doesn't have every single power. That makes it easier to work with. So if we were going to cross multiply and solve this, we get that n has to be greater than or equal to 2000 in order to stay below this. Well, again, remember, we were identifying the error term. So that means n equals 2000 is the error term. So we must go to 1 before that. So must go to n equals 1,999. So in other words, you need to go to 1,999 terms to get the accuracy that we want. So we can apply what we learned in the first half of the unit to any time we have a Taylor series that is alternating. Okay, if it's not alternating, the best we can do is Lagrange error. That's why we have both options. Alternating series error bound is definitely easier, but it doesn't apply in every case if you're not alternating. So let's work with sine, and we want to find the error in approximating sine 1 with a 5th degree Maclaurin polynomial. Well, sine has odd powers, so we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and that's our 5th degree Taylor polynomial for sine. So we want to sub in 1 now, so we're going to have 1 minus 1 over 3 factorial is 6, plus 1 to the 5th is 1, 5 factorial is 120. So if we add those all up, it would give us 1 over 1 over 120. So that is our 5th degree Taylor polynomial approximation, actually Maclaurin because it's centered at 0 for sine of 1. Well, now we want to find the error. So you could use Lagrange, but Lagrange tends to be more challenging. This is alternating, so we can use alternating series error bound. So our remainder, our error, is less than or equal to the absolute value of our next term. So for us, the next term would be our 7th degree term. So it would be 1 to the 7th over 7 factorial. So that's 1 over 5,040. So we know this 101 over 120 is within 1 over 5,040, 1 over 5,040 of the value of the infinite series. So we were fortunate that it was alternating allows us to do this easier error. If not, then we would have to do Lagrange. So if we're going to use cos, we're going to see how many terms we would need to be within 0.001. So cos is even powers, so we have 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, plus dot, 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 dot. And when you sub in a 3, that would really be 1 minus 9 over 2, plus 81 over 24, minus 729 over 720, plus dot, 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 dot. So when we subbed in 3, notice our basic setup is we had 3 to a power over that same factorial for the power. Because when we do alternating series error, we have absolute value. So really what we're going to work with is we're going to work with 3 to the n over n factorial. And we need that to stay less than or equal to 0.001. Now remember, by putting an n, this is going to allow us to identify the error term. And then the term before that is the one that we would have to go out to. Now, the reason it's important to do it this way and not do it like with an n plus 1 is cos is only even powers. So when we go to our table, we're only going to look at the even values. We're not even going to bother looking at the odd values. So let's go to a graphs page. We're going to do 3 to the x over x factorial. So we got 3 raised to the x over x factorial. Hit enter, we'll go control T. So if we scroll down, we're looking for within 0.001, so 1,000th. So not quite there yet. That's pretty close. And remember, we're only looking at the even. So I'm not even going to look at 13. We're going to skip down to 14. Well, now 14 has point and then 4 zeros and then a 5. So that's going to be our first one. So that means that's our error term. So we would need to go out to the 12th degree then. So again, we don't care about the odd ones. So the 12th one was 0.0011 and some other stuff. The 14th was 0.000054. So that means this is the error, meaning this, the one before, is the one that we want. So we need to make sure that it's calculated out when n is greater than or equal to 12, which makes it a polynomial of degree 12. So our final answer would be 12. Now with these, always just be careful if they want the degree or if they want the number of terms. If they want the number of terms, you'd have to count out how many terms there are when you get to the 12th degree. That's it for this video. Have a great rest of your day.